Hi, so in this video, I want to talk about big O notation and I want to teach you the basics of how it works. So, what is it? One common phrase that is used to describe big O notation is how code slows as data grows. It is the analysis of an algorithm's efficiency as data increases. Big O notation is also machine independent, meaning that we don't really care how much time it takes. We're more focused on the number of steps it takes because certain machines can run certain algorithms faster. We also ignore smaller operations. So for example, O of n plus 3, we would just simplify to O of n because we don't really care about the smaller steps. We're looking at the bigger picture. N is also the amount of data. So remember, big O notation we are using to analyze the algorithm's efficiency as data increases, where data is then n. So let's take up an example. So let's say we have a function. We call it add up, and we simply pass in a parameter n, and in this function we just add up to that number n. So let's say that n is 1,000,000. This function will currently take around 1,000,000 steps. This means that this function is O of n, linear time, because the amount of steps it takes is proportional to number n. Now if we can also rewrite this function. So now it is in constant time, meaning that if n is, for example, 1,000,000, it will only take us around 3 steps. So now this function has constant time. No matter the size of n, it will still take us the same amount of time. This means that this function is a lot better than this function because it obviously takes us much less steps. And now even if n was 10,000,000, in this function it will still take us only 3 steps. But if n was 10,000,000, then in here it would take us 10,000,000 steps. That is why this function is better than this. So let's take a look at the graph. So on our x-axis we have the n, so data, so as data increases, and on the y-axis we have time, or the number of steps it takes. So we have O of 1, which is also called constant time. These can be things as accessing a value in an array or adding/removing in an array. Next, we have O of log n, which is also called logarithmic time. One great algorithm that we have also talked previously in this channel is binary search. And if you take a look at the graph, you can see as data increases, it takes less and less and less time. This means that any algorithm that uses O log n gets more efficient as data increases. But if we're only working with smaller data sets, it's not that efficient. Next, we have O of n, which is then called linear time. These can be things as looping through elements in an array, or just finding the max/min values inside an array, for example. And so basically, as it increases proportional, so as the data size increases, the number of steps it takes also increases linearly. Next, we have O of n log n, which is also called quasi-linear time. These can be algorithms such as quicksort, merge sort, heap sort, and so on. And if we take a look at the graph, you can see the larger the data sets, the less and less efficient it becomes. Next, we also have O of n squared, which is then called quadratic time. These can be things as insertion sort, selection sort, and bubble sort. If we just compare between O of n and O of n squared, let's say we are working with a data set of 1,000, so n is 1,000. If we have an algorithm with O of n, this will take us only 1,000 steps. But if we're working with an algorithm of n squared, it will take us 1,000,000 steps. Also, one thing before anyone leaves, a big O notation can also be used for space complexity. So what we have been talking about until now is called runtime complexity. So basically, how much time or slash steps it takes us to complete an algorithm. But it can also be used to calculate how much space in memory a specific algorithm will take. So everything is still the same. All of these graphs are still the same, even for space complexity, but they can also be used to calculate how much space in memory it takes. And there's also more graphs than this. There's, for example, of n factorial, for example, which is even worse than this. And then there's also square root of n, and so on. But these five are the most common ones. And if you know these five, you will get pretty far in the big O notation. But yeah, that is all I had to show you guys today. If you enjoyed the video, or if I teached you anything new in today's video, please make sure to subscribe, give a thumbs up, share, and all of those wonderful stuff. Thank you so much for watching, and I'll see you in the next one.